I'm just going back to the beginning so that all my classes can get this. When we are dealing with measurement versus exact numbers, what we have to look at in our measurements is the fact that there's a lot of uncertainty that comes with our measurements and our expressions of our measurements. For example, when an object's mass is reported to be 32.3 grams, it may actually be 32.4, could be 32.2, but it definitely, we know it isn't 35.1. The number of digits can tell us the precision of our measuring instrument, and we know that a measurement of 32.3 grams is going to be more precise than 32, and those are going to be derived by what type of instrument that you have. So example 1, how should the length of the pencil be recorded for each of the centimeter rulers? Why should the measurement of the same object be recorded differently? So when you are looking at the length of the pencil here, for this one, when you go to record the length, this one is going to have a length of 6 point, and then we could say this is 6.6 centimeters. And for the ruler to the right, when we look at where this falls, we could record this as 6.5, and let's say that somewhere in between, so we could say 6.56 centimeters. So why should the measurement of the same object be recorded differently? When we are recording a measurement, we need to write all the certain digits and exactly one uncertain digit. So our certain digits are going to be what we see on our measuring device. So for this one, our only certain digit is 6. So when we write the measurement of 6.6 centimeters, the only thing that we know for certain is the 6. Okay? The next one, the 0.6, for us is estimated because we see that it maybe falls somewhere in between 6 and 7 and maybe a little bit to the side of the 0.5. If somebody else reads that, they could read it as 6.7. So when we're recording a measurement, we need to record all the certain digits. So for this one, that's the 6, and exactly one uncertain digit. For this one, that's the 6. For the one to the right, when we're looking at where that falls in between, our certain digit is the 6 here, point. And then we also know that that black line right there is a marking of a 0.5. So we know 0.5 is also certain because it is marked on our measuring device. Then we estimate where it's falling. So it might fall 0.56. It might fall in like that. Now, it can change. That estimated digit is going to change depending on how you're viewing it, depending on who's viewing it, because that last digit is your estimated digit. Okay? In a measurement, the last digit, again, is always the estimated or the uncertain digit. And the uncertain digit is always 1/10 of the increments on the measuring instrument. So between a 0.1 and a 0.9 is what it's talking about. So 1/10 of those increments. When we're dealing with significant digits or significant figures, these include all our certain as well as the uncertain digits in a measurement. So when we are looking at the measurements up here, we would say that this, our certain digit is 6, our uncertain digit is 6 here. We would say that this has 2 significant figures. Or we say 2, and we abbreviate this with Sig Figs. So we say 2 Sig Figs. Whereas in the measurement device to the right, we say that this one has 1, 2, those are our certain digits, and then 1 estimated digit. So altogether, this one has 3 significant figures. And you will see that a measurement device that can give you more significant figures in your measurement is going to be a more precise measurement tool. So looking at the difference between exact numbers and measurements. When you have a dozen eggs, contains 12 eggs, and one egg has a mass of 12 grams, we look at the first one to the left and we know there's no uncertainty in that statement. That we know for sure that there's always 12 in a dozen because it's a counting number. So there's 12 in a dozen, that is for sure. There's no uncertainty there. However, when we say that one egg has a mass of 12 grams, there is some uncertainty there because it could be a little less than 12, could be a little more than 12. So what is the difference between an exact number and a measurement? An exact number, there's no uncertainty. There's no estimated digit, so it has an infinite amount of significant figures. For example, there are 24 chairs in this classroom. There's no uncertainty there. You can count 1 through 24. Whereas a measurement always has uncertainty and is reported with an estimated last digit. So, looking at example 3, if the length of an object is recorded as 350 centimeters, sketch the ruler with which it was measured. So, when you're looking at this ruler, you will see that your 3 here is your only definite number that is marked on that measuring device. And then you look at where it falls right here, and you can estimate your 5. But at that point, you have to say that the 0, you have to put the 0 in there because this is 300, this is 400. So we know that the measurement falls between 300 and 400. So that 0 is going to be a placeholder. So the 0 is serving as a placeholder. Now, let's say that the 0 was the estimated digit. Let's say that there were markings on this ruler. And so we had okay. At that point, if we have the markings on this ruler, our 3 is our certain digit, our 5 is our certain digit, and then our 0 is our estimated digit. The way we would express that is we would have to put a decimal place after that 0. That decimal place is solidifying the fact that that 0 there, it lands exactly on point. You have 350 and that 0 is your estimated digit. So when you are counting significant figures in any measurement, you count all of your known digits plus your one estimated digit. Now, what we're going to look at are the rules that we use to determine which digits are significant and which ones are not. And what is in question are your zeros. That's always what's going to be in question. All non-zero digits are always going to be considered significant. So let's say, for example, if we have a measurement that reads 2.54 centimeters, then every single one of these is significant. So we would say that this measurement has 3 significant figures. If we have a measurement that looks like this, and it measures 0.005 milligrams, then lead zeros, which is what you see right here, lead zeros are not considered to be significant because they are placeholders. They're serving as placeholders. And any 0 that serves as a placeholder is not a significant figure. So for this, we say that this one, that 5 is our only significant figure here, so this measurement only shows one significant figure. All right, when we are making a reading and we have sandwiched zeros, let's say that we have 20.5 grams. When we are looking at the 0, which is the zeros are what are in question, we know that if this is setting at 20.5, that 0 had to be a definite number. It had to be a marked number on a measurement device. So therefore, the sandwich 0 count, so this has 3 significant figures. Now, looking at trailing zeros, there's 2 instances that I can look at trailing zeros. Let's say that we have a number that looks like this, and it's measuring 1.50 grams. That 0 here is a trailing 0. But that trailing 0, because of that decimal place, that trailing 0 is significant to the measurement. So therefore, this measurement has 3 significant figures. However, if we had a number that looked like this, and it says 15,000 grams, if we have trailing zeros and we do not have a decimal place present, then none of the trailing zeros, none of these count as significant figures. They count as placeholders. So looking at what counts, the 1 and the 5 do, and that's it. So this number only has 2 significant figures. Now you can see that this number versus this number, this one is a lot more precise in the measuring. And the one to the right leads to the speculation that rounding occurred there. All right, a different set of rules that you can use to determine significant figures. Some people use the 4 rules that I just went over and just kind of memorize them, and some people use this, and this is called the Atlantic Pacific rule. So if you've got the United States here, remember that on this side is your Atlantic Ocean, and on this side you have your Pacific. Okay, so if you're looking at your number and the decimal place is present, you're going to start on the Pacific side of the number, start counting with the first non-zero number that you get to, and then every number that comes after that. For example, here you've got a decimal place that is present, so you're going to go to the Pacific side of the number, which is over here, because this is the number like it's the United States. The Pacific side is on the left of it. You're going to work your way in until you get to your first non-zero digit, which is the 2. That one counts, and then everything that follows counts as significant. So we would say that this number has 4 significant figures. Same thing here, decimal place is present. Start on the Pacific side and work your way in. Your first number you get to is non-zero. So that one counts, and everything that comes after counts. So this number has 4 significant figures. If the decimal place is absent, you start on the Atlantic side of the number and start counting with the first non-zero number that you get to, and every number that precedes that number. So here you have no decimal place, it's absent. So you go to the Atlantic side of the number, work your way in, and do not start counting until you get to your first non-zero. Your first non-zero is the 2, and everything that comes before that counts as significant. So this one has 3 significant numbers. The next measurement down, decimal's absent, work your way in till you get to your first non-zero digit. This is the only one. So this one has 1 significant figure. Okay? Now, keep in mind the implications on your significant figures. The more significant figures that you have, the more precise your measurement was. So when you're looking at the 200 milliliters, you could probably already tell that that is not a precise measurement. So therefore, it only has 1 significant figure. All right, so looking at these as an example, and what I would do is go ahead and pause this, underline and count the number of significant figures in each of the following measurements. But I'm going to go ahead, so pause this, do this, and then play it again to see if you are correct. So, 2.53 seconds. All of these numbers are non-zeros. So all of them count as significant. So this one has 3 Sig Figs. So every time I put the number up here, we're referring to Sig Figs or significant figures. All right, this one here, 2,400 grams. This one has trailing zeros. These trailing zeros do not count as significant. So the only significant figures that I have here are the 2 and the 4. So this one has 2 significant figures. All right, using the Atlantic Pacific rule, if you wanted to use it that way. Here you've got for 0.00241 meters. This one, you have a decimal place present. So go to the Pacific side of the number, work your way in. The first non-zero you get to counts and everything after. So this one has 3 significant figures. Okay? This one, if you're using just your rules, leading zeros in a decimal do not count as significant. Everything else does. Trailing zeros in a decimal count as significant, and sandwich zeros do. So everything after that counts. So this one has 4 significant figures. Trailing zeros, as long as you have a decimal, count. Again, think about it, they make that measurement a lot more precise. So all of those are significant. So this one has 3 significant figures. The decimal place that is put there makes that 0 significant. So this one has 3 significant figures. And using the Atlantic Pacific rule on the whole number that you see at the bottom, the particles, go to the Atlantic side, work your way in, and you do not start counting until you get to your first non-zero digit. And that's this one. Everything that came before counts as significant. So therefore, you've got 14 significant figures here. So if you go back and you look at the numbers that have the least amount of significant figures, like this one, 2,400 grams, then that is not as precise a measurement. Look at the ones that have more significant figures, like this one. That is a very precise measurement. So the more significant figures that you have in a measurement, the more precise the measurement was. Okay, relating significant figures to scientific notation. Scientific notation is a convenient way to report quantities that are very large or very small. However, it is also a very convenient way because every digit of a measurement reported in scientific notation is always significant. So, when we look at the first one, write the following measurements in scientific notation, write the correct number of significant digits. When you put a number into scientific notation, what is displayed at the beginning are all of your significant figures. So you would write this as 2.5 times 10 to the 4th. This has 2 significant figures. For this one, you would write it as 1.30. Because these 3 are significant, they have to be displayed in scientific notation. So 1.30 times 10 to the -3. And this one has 3 significant figures. Now, writing the measurements in standard decimal notation with the correct number of significant figures. Again, everything that is expressed here when you're looking at scientific notation is significant. So all I'm doing is moving my decimal place back 2 places and filling it in with placeholders. So this 0 is just put there to make sure that that is known as a decimal. This is a placeholder, and then everything after this is significant. This has 1, 2, 3, 4 significant figures. Okay? This one right here, you would move your decimal place forward 1. All 3 of those are significant, so this is expressed as 45.2 centimeters, and all 3 of those digits are significant. So everything that is expressed, when you see it in scientific notation, everything that is expressed at the beginning, those are all your significant figures. So it's easy when you see it in scientific notation to determine the number of significant figures, because trailing zeros get dropped if it is a larger number, beginning zeros get dropped if it is a smaller number.